In this video, we're going to discuss how to compute the center of mass of a molecule and how to translate a molecule to its center of mass. So starting off with the concept of mass, we can define various moments of mass. So the so-called zeroth moment of mass would just be the total mass. So being the zeroth moment, that is what we would call a rank zero tensor or a scalar value. So it's just a regular number. And the total mass just measures the resistance to force or resistance to acceleration of a given object. So to compute the total mass, it's a pretty simple formula. We have a sum from I equals 1 up to the number of atoms n of the mass of each of the individual atoms. So sum over all n atoms. Okay, so that's pretty simple thus far. So for atomic masses, we have things like carbon being 12.01. In most cases, you really should use isotope masses. So the mass of carbon-12 is 12.0. Mass of carbon-13, much closer to 13. I'm not going to use isotopes in this case. Number one, because I'm not a spectroscopist and I don't care that much about the values. And number two, it's easier just to use the regular masses and not worry about isotopes. But take note of that caveat that if you showed these values to a spectroscopist, they would probably freak out and then go on a tirade against you. Okay, so hydrogen 1.01, oxygen 16.00. These are just the values I would look up off of a standard periodic table. And those units all in atomic mass units, AMU. Okay, so those are examples of things that are in the set of atomic masses. All right, and just for good measure, we'll remind ourselves that one atomic mass unit is equal to 1.66054 to 6 significant figures times 10 to the minus 27 kilograms. So a very, very light object. It's approximately the mass of protons and neutrons, but it's somewhere in between those two, as one of them is slightly heavier than the other. Okay, and again, note we should be using isotope masses, but I'm lazy. All right, so that's the zeroth moment of mass. Our first moment of mass is the center of mass. So that would be a rank 1 tensor, or what we would also call a vector. So it's a vector that has as many dimensions to it as the dimensionality of the space in which we are computing it. So we are primarily interested in 3-dimensional Cartesian coordinates, so we will have a 3-entry vector. So our center of mass is a vector which has 3 entries: the x-coordinate of the center of mass, the y-coordinate, and the z-coordinate. Makes sense, x, y, z. So far, so good. So the values of these are all going to be 1 over n, sum from I equals 1 to n, and this sum is the case for the other values as well, but let me just put dots there again, because as we've noted, I'm lazy. So I have the mass of atom I times its x-coordinate, sum again, mass of atom I times its y-coordinate, sum again, mass of atom I times its z-coordinate. Okay, so that's how we actually get the value for the center of mass. So that'll be a 3D Cartesian point or a vector, whichever you prefer to view it as. So for example, as I said, with Cartesian coordinates x, y, z, we have 6 redundant coordinates. 3 of those are translations. So if we give our molecule the constraint that we're going to move the center of mass to the origin, then we can remove those 3 redundant translations. So we can have translating to the center of mass back up there, removes 3 redundant coordinates. And that's nice because if we want to do that, we can more easily compare whether or not two molecules or two structures are the same, or by how much they are similar or different. Okay, so in order to do that, we just have to translate all of the individual Cartesian coordinates of all the atoms. So for example, xi, if we translate to the center of mass for atom I, yi, zi. So the xyz coordinates for a given atom I, if once we translate to the center of mass, is equal to the original xyz vector, its original coordinates, minus the values of x, y, and z for the center of mass. So that is just a vector subtraction, which is vector addition times -1 for the second case. So that vector is just xi minus xcm, yi minus ycm, zi minus zcm. Okay, so that is the center of mass. So let's do a demo here. So if I can bring up in Avogadro, I've got a benzene molecule here. So 12 atoms, 6 carbons, 6 hydrogens. Center of mass in this case, if it is very symmetric, the point group of this molecule, if it is perfectly symmetric at its minimum energy geometry, would be D6H. In that case, the center of mass would be at this ring centroid point right there. But currently, that is not the origin. So let's do some calculation inside of Jupyter and see what's going on there. Okay, so those are the coordinates, the XYZ coordinates, 36 coordinates for the 12 atoms. We have center of mass here, which is the program which I have added on to from our previous videos. You'll notice now we have an extra dictionary here defining the atomic masses of the elements in AMU. All right, what else do we have here in terms of new functions? We have printing the center of mass. Obviously, we need to print those values. Same math functions as before, pretty much. I have a new function for translating coordinates. So taking all the coordinates and then translating them away by a vector times a scale factor. So in this case, I put the center of mass for the vector, and the scale factor is -1 because I'm subtracting out those coordinates. I have a function to get the center of mass, doing those 3 additions that I showed in our original part of this video. And then let's see. So in our main block, now we have this, again, with 2 extra lines, getting the center of mass from the geometry and printing out those values. Then at the end, I'm going to translate the coordinates to the center of mass and print out the geometry again. So I've done that here. I've executed this. The command was called center of mass. Again, all these geometries and these programs are available on the GitHub. Links in the description. We have the initial geometry, 12 bonds in angstroms, 18 bond angles in degrees, 24 torsion angles, all either -180, 180, or 0 because it's a planar molecule. All the out-of-plane angles are pretty much 0, except for a little numerical noise. Then we have our center of mass in angstroms, XYZ coordinates. There they are. And we have translated our molecule to that center of mass. If you compare here the values, -0.26 versus the 0.25 it ends up being, that's because we translated by -0.52, adding 0.52 there. Okay, so that is the basics of center of mass for molecules.